Hi everybody. So this is going to be just a rehash of what we did on Friday with PDF and CDF functions. So we'll go ahead and get started. First thing I did on Friday was I wrote down the following information. We talked about PDFs first, and that stood for probability distribution function. And then I told you CDF stands for cumulative distribution function. Okay? A PDF is the function you want to use when you're finding the probability of exactly some certain number of successes. A CDF function is what you're going to want to use when you're trying to find the probability of a certain number or less of successes. So that might be a little confusing. So let's talk about the binomial random variable again. Let's say x is binomial. And with that we also have to say how many trials there are, n, and what the probability of success is. So for shorthand in class, what I'm going to do is write it like this. If x is binomial, I'll go ahead and abbreviate it like this, and I'll put numbers in for n and p. So in our example with looking at the number of girls that you have and 4 kids, x was binomial, 4 tries, with a probability of success of 0.5. Okay, so in class, I then laid out all of the possible outcomes, 0, 1, 2, 3, and 4, like this. Okay? So if the outcome was 0, that would mean we had no girls out of the 4 kids. This would be 1 girl, 2 girls, 3 girls, 4 girls. And when we did the experiment in class where you simulated that with the calculator, it ended up that 0 was pretty small. It didn't happen very often. 1 was more. 2 was most likely the most. The most you got were 2 successes, or most of the time you got 2 successes out of the 25 trials. If we had taken all of our answers or all of our numbers and added them all together as a class, so we would have had, I don't know, something around like 500 or 600 different observations, what we would have found is that this distribution would have been pretty close to being symmetric. 2 would have been the most. 1 and 3 would have been the next most. 0 and 4 would have been the least. And that's just an illustration of the law of large numbers again. The more trials you have, the closer the closer the numbers are to the actual probabilities. So that was the basic beginning of it. So then I said, okay, there is a way to do this so that you will always get it right. If you do this way, when you're finding probabilities of binomial random variables, you won't make any mistakes. And I know everybody wants to do that. They don't want to make mistakes. So I'm going to go ahead, flip the page. And as an example, let's suppose x is a binomial random variable where n is equal to 10, probability of success is equal to 0.5. Okay, now this is different than the last example. New random variable, new scenario. The way you do this is write out all of the possible ways that you can get an outcome with this random variable. If x is the number of successes in 10 trials, we could possibly have no successes, or we could have 1 success, or 2 success, or 3, and so on, all the way up to 10. And each one of these numbers of successes out of 10 has a probability. The cool thing is that your calculator can do the probabilities for you. Okay, but before we get to the calculator part, here's the way that you can set it up so you won't ever make a mistake on it. Okay? And the way I started was this. Suppose that you're looking for the probability that x is equal to 2. Okay, the first thing you want to do is read that probability statement. Probability x equals 2. And then what you do is go ahead and circle, and I'm going to highlight here because I can do it on the board. I'm going to highlight what that means. The probability that x equals 2 is that one right there. Okay? The PDF function will compute probabilities of having exactly some certain number of successes. So in the calculator, we will use the PDF function of n, p, and then we're looking for the number or the probability of 2 successes. So that's the way it'll look in the calculator. There'll be a binomial in front, but I'll show you that in just a second. So a PDF of 10.5, so n and p, and this is the number of successes we're looking for the probability of. We can do the same thing like this. Probability that x equals 5 equals PDF of 10.5, and what number should go here? Yes, it's a 5. Let me take care of that bouncing icon. My printer just ran out of paper. So that's how you use the PDF function. What you're looking at is just finding the probability of exactly a certain number of successes. Okay? All right. Now, let's take a look at a probability statement that looks something like this. What's the probability that x is less than or equal to 4? Okay? First thing you need to do, again, is go ahead and highlight or circle the numbers that you're looking at the probability for. So let's go ahead and take this. If I'm looking for less than or equal to 4, that's going to be these numbers right here, less than or equal to 4. And guys, understanding the language of this, what this means, that's the critical part, because that's how you know what to circle and or what to highlight. Okay, x is less than or equal to 4 means 4, 3, 2, 1, or 0. We're looking for the probability of having 4 or fewer successes out of 10 trials. So, this is where the CDF function comes in. The CDF function has the same format as the PDF function, except the CDF function accumulates the probabilities. So in other words, it adds them all up. So the CDF of 4 is going to take the probabilities starting at 0 and adding them all up to 4. 0 plus 1 plus 2 plus 3 plus 4. All of these probabilities get added. CDF functions always start with 0. They always add up probabilities from 0 up to the number that you're putting in the function. Okay? Quick question. What would the CDF of 10 be? That's right. The CDF of 10 would be 1, because you're adding up all of the probabilities. Since this is the entire sample space, then the probability of all of them would have to be 1. How about this probability? Probability that x is greater than or equal to 6. Okay, first thing you want to do again is highlight it. Let's go ahead and move this. Greater than or equal to 6 means 6 on up to 10. Now, here's the problem. The CDF function can't add, or can't start at 6. It always starts at 0. Okay? But we can fix that pretty easily. All we do is just make a different box. Oh, wrong colors. Not what I wanted to do. I wanted to do black border and yellow. There we go. Okay? So here's how we can set that up. If this is what we're trying to find, we know the CDF of this we can find with the calculator. We know all of it equals 1. So we could find this out by doing 1 minus the CDF of 10.5 and 5. Okay? And how you know what numbers to put here and here and here is by looking at the drawing, and that's why the drawing is so important. And by doing the drawing correctly, you need to look, or to do the drawing correctly, you have to look at the statement. The statement is the key to that. Okay, I'm almost at my 10-minute limit, so I'm going to stop this one, and then I'll go ahead and continue with part 2. So look for part 2 on YouTube shortly. No, actually, probably is there already.